In this video, we're on number 4 here, and we're going to look at evaluating logs. And we really need to make sure we take into consideration any restrictions. Whenever there's a variable involved at all, think if this is true for all x's or just certain x's. So think about this from a function's perspective. Is this a composed function? And do I need to look at the domain of the inner function? All those kinds of things. So really pay attention to that to get full credit on all your parts of things. So here we have evaluate log base 3 of 3 to the x. And that equals x, right? So because this, remember, we have this property that log 3 or base 3 of 3 is going to equal 1, right? So then that just leaves us with x. And is that true for all real numbers? In this case, yes. So this is x. It's an element of all real numbers. So we're going to start stating the domain when we're solving for x. And same thing here. If we have log base 10 of 10 to the 2 minus x, right? That just leaves us with the exponent. That equals 1. Kind of putting a slash there, just showing that equals 1. But however you want to mark that, you can. So that's going to equal 2 minus x. And again, we can have exponents equal to any real number. So that's going to be for x as an element of real numbers. But now if we look here at 2 to the log base 2 of 8. Okay, so with this one here, 2 log to the log base 2 of 8, we don't have a variable involved, so we don't have to worry about the restrictions and think about them. But I just wrote a little note here for you. Whenever there is a variable, then state the domain. So that'll just get you in the habit of that. So now let's look at some patterns going the other direction, like where there's a log in the exponent as the exponent. So can we develop some properties based on the patterns that we see here? We're kind of just going the other direction. So we're taking this exponential and we're going to put it in the log form. So again, let's write our thing up at the top here, our little pattern that we have. Y equals b to the x if and only if log base b of y equals x. Okay, so this is a little bit different here because we have our exponent is actually a log, but we're going to write that as like the x, right? So this is like our b to the x. So our x is log base 2 of 8, which we could write as 2 cubed. So I'm just writing that a little bit differently here. So I'm writing it as 2 to the log base 2 of 2 cubed. And then I know I can use my properties from before. So then I know that log base 2 of 2 is actually equal to 1, right? So then I'm left with 2 cubed, which equals 8. So this whole thing here, 2 log base 2 of 8 equals 8. So notice this pattern and how that kind of just undoes. That's because we have an inverse operation happening. It will become just 8. Okay, so we're left with that exponent, if you want to think of it that way. So if we now have e to the ln 1 over e, this would be equal to e to the negative 1. So it's like ln e to the negative 1, and then we're undoing that. So we have e, or this is all negative 1. So we have e to the negative 1. And then we have that would equal 1 over e, which is what we have inside here. Now again, this is like to a 10. So what do you guess this one's going to be? So we have an exponent raised to the log of that same, or sorry, a base raised to the log of that same base. So that's going to undo itself, right? So we'll be left with 100. So we have a pattern here that we could write as, or property, as b log base b of x will equal just x. So you should write all these properties out on a piece of paper. I do think I have something that I can post for you, or it might already be up there, but just so you keep that in mind. And then we also, whenever a variable is involved, remember that will only work for when x is greater than 0. Okay, because that's what has to be true for logs. Right inside there, we can only have greater than 0. So make sure you state the domain for that. Now this, these others you could try, pause the video, try as classwork. Some are a little trickier than others. So I'm definitely going to walk you through it. But if you want to pause and try them, then go ahead and do that now as classwork. But I'll put kind of a question mark, just try. All right, so we can apply our property, and if we have pi to the log base pi of 17, we just end up with 17. If we have a half raised to the log of a half, we'll end up with just x. And in this case, because that started off as a log, we have to have x greater than 0. Remember, if there's a variable involved, we have to do that. Pi is not a variable, so we're good there. If we have this one now, 5 raised up to the log base 5 of 2x plus 1, we'll just have 2x plus 1. However, again, we have to know when that's what the domain is. We need to set domain. So we don't want this equal to 0. So we have to find 2x plus 1 and set it not equal to, we want more than not equal to 0. We want it greater than 0. So we have 2x greater than negative 1. Divide both sides by 2. X would have to be greater than negative a half. So we have to set that over here. Again, don't forget whenever there's variables involved. Now on this one, we're going to have 3 minus x. Now this is an exponent being raised up. It's not written as a log there. So we're good. That can be all real numbers because this is an exponential side there. So as long as x is a real number, we'll be fine with that. That'll always come out to be a positive value inside where the log is. Okay. Now we just have one more page with the graphs. Just want to take a quick look at this. And if you're familiar with your parent functions from your exponentials, then you'll know that inverses, remember, reflect on y equals x, right? So it's kind of not the best line. Let me get a better line. So if we're starting with f of x equals 3 to the x, that's this right here. And if you recall, we always have the points, we have a -1, and then we'll have a 1 over our base, so we'll have a 1/3 as a point. And then we'll have, so that's probably like right here. And we'll always have 0, 1. And then we'll always have 1 and whatever the base is. So for our inverse, we just, again, we want to swap them out, right? So we would have, let me just mark this as f of x here. So for our f inverse of x, we're going to have the value 3, 1 right there. So I'm going to go slow with this. You can do it yourself as I'm doing it. And then we're going to have the value 1, 0. So again, we want 3, 1. We want 1, 0. And then we also want 1/3 -1, which would be right about here. Okay, and I know I'm going to have to approach this axis to be symmetrical over y equals x. And then this kind of just goes off that way. So remember, this is y equals x. So we have symmetry the same way we do for other functions. So this is our f inverse of x. Okay. Now we have g of x over here. So I want you to try that for classwork. It's 1/3 to the x. So it's a little, different layout for you. So I wrote this up the top here that recall that for b to the x equals y, when we have an exponential, we have the points -1b, 0, 1, and 1b. So it will go through that. Now for its inverse, we are going to exchange the y and the x, remember? So then we have the log will go through the points 1 over b, -1, 1, 0, and b1. Okay, so I drew that graph right here so you can check against mine. Now remember here when we're talking about 1 over b and -1, that's down here. B was 1/3, so 1 over 1/3 is 3, and so on and so forth for the other values there. Now these last two are things that we're going to use transformations for. So let's take a look here. We have sketch m of t equals log base 1/4 of t minus 2. So we're going to want to get the parent down there using those key points. Okay, so what I've done here is sketching m of t equals log base 1/4 of t minus 2. So I know I can't have t equal to, I have to have it be greater than 2. So I'm going to have an asymptote there for my transformed graph. But first I want to look at the parent, and I know I have to have an asymptote here. I have a vertical asymptote at t equals 0. Okay. Or x, whatever you want to call it, but I think this, yeah, we're in t and m of t. So I use the key point, so 1 over 1/4, -1, that's right here, for -1, 1, 0, and then 1/4, 1. So I plotted that right here. Okay, following along my asymptote. Now I know I have a shift right here. So this is a shift right 2. And so that means my vertical asymptote is now going to be at x equals 2. So I'm going to make a dashed line here, and now I have vertical asymptote, or t equals 2. And then I want to plot my points. So all these are just going to move over 2 units. So let's see if I can get that in there pretty easily. Okay, so I just shifted these over by 2, so my 1/4 is now 2 1/4 1. My y stays the same, right? So 1 becomes 3, and my y is 0, and 4 becomes 6, and my y is still -1. So I just want you to note the scale every couple of blocks here, so it's marked off. So I'm going to approach that as an asymptote and then just come in, sketch it in. You don't have to be perfect, but marking down some of the key points, like if you had the 6, -1 labeled, the 3, 0 labeled, and the 2 1/4 there we go. And that is graphing using transformations. So we also have the natural log. We have part B. If you want to try it on your own, you'd have to graph the natural log in there, just like you did for your previous sections in the exponentials, right? So except it's its inverse. So it's going to reflect on the across the y equals x, so we're writing it as a natural log. So that'll be a little bit different. It's just all changed around. Then we also have this situation going on here. We have a -t, so we're going to flip over the y-axis, and we're going to have a vertical stretch of 4. Okay, so go ahead and try those. You can use the, sketch the parent first, or take it in stages, however you want to do that. Okay, so here I've drawn in my parent. I use these values, just using, again, that same pattern of the 1/b and -1 as a point, 1 0 as a point, and b and +1 as a point. And then I actually added in another one just for good measure. I did that over here too. So now we can do our flip. So that means all our x's are going to come over to the other side here, so it's just going to reflect this way. Just flip over the y-axis, and I'm just sketching here, so it's not perfect, but that's okay. And then I'm going to stretch, so I'm going to have a vertical stretch of 4, so I'm going to multiply all these y values by 4. So I'm just going to squeeze that in here, and so it's going to look something like this, just stretching a little over this way. Whoops. Okay, so you would just have 1/e. It would become, it would actually become -1/e. -4 would be a point. Okay, and then we would also have -1 0 as a point. Okay, so we're still kind of going through that. Let me just get this a little better. Here's our -1 1 over e is like 2.7 something. And -4. So I'm kind of more, whoops. That's -1 over e, sorry. And then -4 is down here. And then I have my other one would be my negative e and my positive 1, which becomes 4. That's what I'm trying to plot here. Negative e would be right about there, and 4. And so then I can draw that in a little better. And then I would label my few points here would be the -1 over e, -4, -1, 0, and -e, 4. Okay, so that is n of t right there. And we keep the same asymptote because we don't have a shift. So I hope that's helpful and you get the idea of this. It does take some practice. You have to combine a whole bunch of skills. So it's really great review of everything we've done so far using a multitude of things. So get into your homework now. From this, it covers sections 4.3 and 4.4 actually in our curriculum, and so they're separate sections. So this is kind of a lot of videos, but it covers 2 sections. Have a great day.